thanks a lot, and thank you for the invitation. So it's the first time I'm visiting Cornell, and I guess it's the right week because last week would not have been so much fun. But it's a great place, and I really enjoy it here. So what I would like to do today is give a very basic type of introduction to some of the mathematical concepts that are important for the study of many body problems. So I'm going to start with a canonical example which has been known for a very, very long time. So this is Newton's dynamics, okay? Basic Newton's dynamics. So I have n particles, which I'm always going to assume are points in this talk. And so they are identical in the sense that each has the same properties. So you can exchange two particles and you have exactly the same dynamics. And therefore, all the information about a particle is given by its position and its velocity. Okay? And then, again, this is classical Newton's dynamics. You have derivative of the position is the velocity, and derivative of velocity is the acceleration, which is the force applied on each particle. And here, again, I'm putting what is probably the first example in physics of such a system, going back to Newton. This is a 2-by-2 interaction. So you see that the force acting on particle number I is the sum of all the forces that particle number j produces on particle number I. And the most canonical example, again, is what is called as the Coulomb interaction, which in general is like that. So the kernel here derives from a potential, and the potential is given by this. As long as d is different from 2, if d is equal to 2, it's a logarithm instead of a power. This is Newton's dynamics as it's very basics, okay? This is a gravitational force, and what you have here is a system of n objects interacting through gravitation, and this is it. So that's the case alpha strictly negative. The case alpha strictly positive, then it's what is called as electrostatic interaction, and now those particles are typically ions or electrons. So those are certainly the two oldest examples of this kind of systems. As I was saying before some of you arrived, when I was preparing this talk, I had many choices to make, and one of them was how much time do I want to spend presenting to you the variety of problems and of systems that you can have of this type, versus how much time do I want to introduce the mathematical concepts. So eventually I decided for presenting the mathematical concepts, which means that I will not show you many examples of this. But certainly there are many other type of kernels like that. In addition, you might say, why only 2-by-2 interaction? You could have 3-by-3 interactions. The problems and the theory would essentially be the same, but you could even have more complicated type of objects, because I could add a control to this, right? And then we are entering something which is very popular now, which is called mean field games, for instance. There's a last question here. So let's remain in the framework of gravitation, right? Then there's a physical constant in front of all that. Okay, and that physical constant is, well, a gravitational constant times mass to the square, right? That's the gravitational force, divided by mass, because you have to write an acceleration. So here there is a number which is gravitational constant times mass. So why am I saying that this number is 1 over n? Because certainly if you're doing astronomy, the mass of an object does not depend on the number of objects that you consider, right? It's an interesting property of the object. So what's going on here is that there are rescalings that I have that I have hidden, okay? And you can do a rescaling in position, you can do a rescaling in velocity, and you can do a rescaling in time. If you want to keep this form, however, you're a little bit limited. And moreover, there's an initial condition here. So if you want to rescale so that all the positions initially are of order 1, all the velocities are of order 1, and you keep this, then that's it. There's no more margin that about what you can do. So in general, after this rescaling, you do have a constant here, and this constant still has no reason to be 1 over n. The conclusion of this rather elementary discussion is that there are many scalings in this kind of system. And this is only one of them. However, the big point here is this is the first one that is actually interesting. So I have a sum of n minus 1 term here, which hopefully I will be able to show they are of order 1. That's actually a big problem, but hopefully this is what you will show. Therefore, if here I have a constant that is really much smaller than 1 over n, the conclusion is I'm expecting that this fourth term will be negligible. And I have a not very interesting dynamics where trajectories are simply straight lines. So that's not great. If the constant here is larger than 1 over n, then I'm expecting that this fourth term is actually very large, and then I'm entering the realm of large field problems, which is probably very difficult. So the critical scale for the coefficient, where you actually see something that is not uninteresting, the first such critical scale is where the constant is 1 over n. And this is called the mean field scaling. That's what produces a term of order 1. As I was saying, there are many variants of such problem. Another one that I will talk about during this presentation is this case with Brownian motions. So now here I'm assuming that there's a little bit of diffusion in the particles, such as random collisions against a constant background. If you have electrons, for instance, a constant background of ions, they may collide randomly. And this will produce a Brownian motion here. In that case, only in velocity, right? So there's no diffusion in the position. And the Brownian motions are typically assumed to be independent. So this is generally called the phase space case because you have position and velocity, phase space. But you do find similar problems written directly at the macroscopic level, in which case you have a first order system instead of a second order system as here. There are many similarities between the two and also many differences. So this will be one of the things that I'll try to show to you in this talk, why this is not the same as that. And in particular, what I can say immediately is that this is a lot easier, which might not be obvious to you now. And same thing, I can consider it with diffusion. And what's probably even less obvious to you now is that that case with diffusion is a lot harder than the same case without diffusion. And in general, there's no reason why the Brownian motion should again scale at order 1. So in general, there is a scale here that we also would have to take into account. And typically what happens is that this is going to 0. That's probably the most difficult situation where you have something like that. So starting from this problem, there are a few typical questions that you can think about. The first one, if you're studying gravitational objects, is why don't the system collapse? Okay, why don't they all go to the same point? So this is the question of well-posedness for a finite number of them. I'm not trying to take n very large. I'm simply asking what's going on. Okay. So I take free bodies, the famous free body problem, and then I'm asking you, why do I have a solution for all times? A somewhat related question, so that's a mathematical version. A somewhat related question is, how do I get stability estimates for this kind of problems? So stability estimates is a big, you can think of many ways of formulating this question. But essentially what this means is, let me take two solutions which start from close enough initial data, and then I want to see how close they are remaining a long time. And of course, I can ask the question for a finite time. I can ask the question for time going to plus infinity, and you have strong stability, asymptotic stability, various type of concepts. But the comparison between the two, I will show you an example. It's very interesting, and it's where you see that even a small n here, if you're not careful, you can easily write mathematical results that are mostly empty from any practical point of view. Okay, so the main question I will try to address here is the mean field limit. So the mean field limit is what's happening when the number of particles increases. Okay. And then you don't want to solve a discrete problem anymore because it's too costly and you don't know what to do with it. So what you would expect is that there's a sort of continuum equation that gives a good approximation of a discrete problem as n tends to plus infinity. You want to find this approximation, and you want to justify that it is a good approximation. So I will only talk about that. But the interesting questions don't stop here. So I quote only a few of them here, but again, I will essentially not address at all during this talk. Okay, so before going further, I would like to mention the first question, which is, you're saying n tends to plus infinity. What does that mean? What is the scale of the number of objects that you have to consider in this model? So this is a model that is actually used nowadays in cosmology and in astrophysics. And then the reason is that at large scales, the universe is mostly dispersed. So relativistic effects don't play such an important role. So this is actually the model I showed you with Newton interaction is actually used to calculate galaxy formations, for instance, by astronomers. And when people, typo here, when people are doing this, how many particles do they consider? Well, there's a wide range. The lower hand is typically around 10 to the 10. But at the scale of the universe, it can easily reach 10 to the 20 or 10 to the 25. And some astronomers are even using models of dark matter. So dark matter is a good candidate for that because it's supposed to only interact through gravitation. So I didn't put any other force in the model, and then dark matter is supposed to follow exactly this. And some models of dark, so this is a very, controversial subject, but some models of dark matter use up to 10 to the 60 particles, so that's a horribly large number. In other applications in physics, n is typically of the order of the Avogadro number. So plasma dynamics is a very good example. And then you find yourself for 10 to the 20, 10 to the 25. So for the moment, I've only talked about this system coming from the application. But there's another use to that, which is let's use this kind of system of ODE to calculate things. And it's exactly the other way around. I found the continuum equation, and now I want to calculate an approximate solution to it. And so I go back to a system of particles, whose particles now are completely artificial, people are talking about metaparticles in a case like that. And you solve numerically the system of ODE, and you think that this will give you a good approximation to your continuum limit. So there, the number is essentially limited by how much you can put in a modern computer and still get a result in a reasonable amount of time. This is actually a very difficult problem, because if you're not careful, calculating the interaction will cost you n squared, and then you're dead. So this is the object of all what are called fast multiple methods and all this kind of things here. If you're doing things correctly, nowadays this is the order of magnitude of particles that you can put and still be able to compute things. And other than that, as I was saying at the beginning, there are many other examples of applications to this kind of things in other fields of science. So a big example is biology or life sciences. Now, those particles now are typically microorganisms, cells, things like that. And if you're thinking, for instance, how many, if you have cancer or if you have a disease, how many bacteria or tumor cells you should consider in a system like that, then that's the order. Typically 10 to the 6 is the moment when we can start detecting some external agent in your organism. And but it can really go to 10 to the 12 when the infection is full scale. And other applications have far lower of those. Now, they are not called particles, they are typically called agents in this case. So social science or economics, then the numbers is far lower than that. And 10 to the 3, it can be a little bit larger than this, but 10 to the 3 in economics, for instance, is a good order of magnitude. Be 10 to the 4, 10 to the 5. So this is how large n can be. And as you see, this forces us to be a little bit careful, because at those scales, you really readily believe that we are very close to whatever limit exists. At that scale, well, maybe not so much. Okay, so let me start with some basic comments. Now we're entering a little bit the math. What can I say about the well-posedness of a system of ODE or a system of SDE? Well, ODE, we have the Cauchy-Lipschitz result, right, 19th century, which tells you that if the interaction is Lipschitz, then you're good. Oh, and let me, right. So this is the interaction there. So that essentially means K is Lipschitz. In the SDE case, well, we had to wait a little bit more, but the Lipschitz case was essentially treated by Ito, so it's reasonably classical as well. But those are not the interesting cases. Right? You have seen that the example I've given you, gravitational interaction, K in dimension 3 behaves like 1 over x squared. We are very far from being Lipschitz. And if K is singular, now it starts being relatively difficult. Nevertheless, this is a simple mathematical result that tells you that if the potential is repulsive, then everything still works. So the repulsive case is the case of electrostatic interactions, right? You have a cloud of electrons and they interact one with another. They all have minus charges, so they are not attracted, they are repulsive forces. In that case, you have an energy, and the energy is just like that, okay? So this is the kinetic energy, and this is the potential energy, and I've written the three-dimensional case. And I've rescaled the energy such that the whole thing is now of order 1, right? So you see it here, some over I, but 1 over n. So this is of order 1, if each velocity is of order 1. And same thing here, I have n squared term. Okay, so if alpha is positive, then that means that each of this term is bounded. So it cannot blow up. And therefore you obtain an information about the minimal distance between any two particles, which scales like that. So mathematically, even though the interaction is supposed to be singular, it's only singular when two particles are very, very close, and they can never collide. So you have well-posedness. Because over the domain of the dynamics, the force is in fact Lipschitz. Now I will show you what happens with this estimate when n tends to plus infinity, and this will be fun. Already you notice that the thing here goes to 0. So if you're not in a case like that, then I'm not going to say anything about it. You have several theories trying to do this. Let me just mention for those who are interested that in the gravitational case, we do not know whether the system is well posed if the number of particles is larger than 4. So that shows a little bit the difficulty that the first, essentially the first dynamical system that was ever written, we still don't know much about it for 5 objects. All right. So let's go back to the Lipschitz case, and I'm going to show you a very nice theorem. So I'm assuming that case Lipschitz, and let's consider the macroscopic case with diffusion. So I will give you a few examples, sometimes with diffusion, sometimes without diffusion, to show a little bit what's going on. Then I have a very nice control on each individual trajectory. Right? So let's consider 2 solutions to the same system, which means that they simply have different initial conditions. Then I control the maximum distance between the two in terms of the maximal distance initially times some exponential growth that is completely explicit. The estimate is completely independent of the number of particles as well, which is great, right? Because if I have an estimate with coefficients which depend on n, and n is 10 to the 20, then I have every reason to be worried. Again, the big problem here is this Lipschitz assumption, which is not reasonable. Right? And how do you do that? Well, very, very simple. You take your 2 solutions and you make the difference. You make the difference, you kill the Brownian. They are gone. Then you just have to compare that. Well, you see that those are exactly. So now I'm using the Lipschitz bound on K. So this is, right, L infinity norm of gradient K times, well, the difference between those 2 terms, which is like that. You take the maximum here. This, you get it there with the 2, because I have 2 of them. And now if you take the I such that this was at the maximum distance, then you have this. So finally, you have a very simple Gromel estimate that you can. So this is an extremely simple proof. If the coefficient here depends on xi, which can happen as well, then you have to do something a little bit more complicated, and you have to follow Ito's instead of what is essentially Cauchy-Lipschitz. But you get the same type of result. I mean, now the control is probabilistic. Here it's event by event, so it's really very. Okay, but now that I have done that, I can come back to my well-posedness result that we were very happy of in the repulsive case. And I can ask, okay, so we are in the repulsive case, and I want to deduce a stability result from that. Because essentially that's what we are hoping mathematical well-posedness is here for, right? It's to guarantee that if you solve a system and you start with points that are fairly close enough, then you will remain close enough. If you want to put it in a computer, that's the minimum, because you will always have a little bit of numerical error, truncations and things like that. You want to make sure that those are not amplified too fast. So let's look at that, okay? So I have this estimate on the minimal distance. And the gradient of k behaves like that. So now I plug that into the gradient of k, and I have something which is polynomial in n to the power 6 in dimension 3. I put that into the stability estimates that I had, and you get this. Which, of course, shows well-posedness from the mathematical point of view, but also shows that this result is completely useless. And I'm not talking about n is equal to 10 to the 3, right? We are talking about n equal to 10 here. That completely blows up to your face. I mean, an exponential of constant times a million, you know. This is pretty big. So completely empty as a result. So this well-posedness case in the repulsive case, it's not there for any practical purposes. There is no satisfactory answer, even in a case like that, concerning the well-posedness. Of course, what happens in the gravitational case is when you put two of them and we have explicit solution, you see that you can have blow up. Because if I put two and I send them exactly one against the other, then they will collide, and that's it. End of my equation. But this is very unlikely. If I perturb just a little bit, then I don't send them. So what we would hope is to have well-posedness in some statistical sense, saying that for most initial conditions, the system is well-posed. This is exactly what people are trying to do. This is exactly what they cannot do for n larger or equal to 5 in the gravitational case. Now I'm going to forget about well-posedness, and I'm going to pretend that I have a satisfactory result there. And I'm going to go to the next question, which is we're hoping to have a continuum limit, but we start from a discrete system. How can we compare a discrete system of ODE with a continuum equation? And that's what I want to do in this section about formalism. Okay. So what we have now is initial conditions, right, which I write like this. And I'm considering a sequence of them, meaning I'm going to let n tends to plus infinity now. So for each n, I have initial conditions, and then take a sequence. And therefore, I have a sequence of solutions with corresponding data. How can I say that this converges toward anything? Here's a simple way. You define what is called as the empirical measure or the counting measure. It's the counting measure. We don't have this normalization like that. Now, this is a very simple object. The measure, right? So Fn of any set in phase space is simply the proportion of particles that belong to that set. That's all it is. But now you've done something very smart, because you had a problem which was not defined in a fixed dimension. You see that this is a very large vector and that the dimension of the vector increases with n. So this is difficult to handle, and I don't know what the limit of that is. And now I reduce it to something which is defined on a fixed space. This belongs to the space of radon measure on whatever underlying space. So this is in RD, this is in RD, this is radon measure in R to the 2D. So now instead of studying the limit of that, I can try to study limits of this sequence of radon measure. And the question becomes, can I show that they have a limit? And can I identify the equation satisfied by the limit? And if I'm doing this, then I will have solved my problem. Just a few comments. First of all, you might say when we are defining this, we are losing information, so that there is more information here than there are there. Not true in general. As long as the particles as what are what we call undistinguishable, which is the case in my problem, then there's just as much information here as there. The only additional information that you have here is the order in which you take the position of the particles. So this defines that vector up to a permutation. If all particles are the same, then the dynamics is invariant under permutation, and therefore you don't care about this permutation. So just as much information here as there. No loss. Second, this might not be such a simple object. In general, this will be a stochastic object. Right? If those guys solve an SDE, then they are not deterministic, right? They are random variables, and so therefore this is a random measure. Actually, even if I don't have Brownian motions embedded into my dynamics, I may want to consider random initial conditions. And therefore, this will again be random, just the randomness carried over the image of the randomness by the dynamics.
Are you generally interested in weak convergence?
Yes, so you're not going to expect any strong convergence on this kind of objects. Even though I'll try not to go too much into the technical details, but do interrupt me if you want to have a precision, because again, I really try to do something a bit basic here, so don't hesitate if it's too basic and you want to ask me something additional. When you're doing this, thing starts very well. If I'm looking at my original problem, and it starts very well because actually the empirical measure satisfies a closed equation. Actually satisfies a closed equation. So you take my first system in phase space deterministic, you put it into the formula for the empirical measure, and this is a small exercise in distribution. You can check that in the sense of distribution, this equation is satisfied. This is called the Vlasov equation. Because, so the Coulomb case then is called the Vlasov-Poisson equation, and this was derived by Vlasov in the 30s for plasmas. So now, your candidate for a limit is very obvious. If this satisfies an equation as n tends to plus infinity, I'm going to extract weakly converging subsequence, and I'm hoping that the limit of those weakly converging subsequence will satisfy exactly the same equation. What happens now if I'm looking at the case with Brownian motion? Well, something not so different. So first of all, you have diffusion, okay, not a big surprise. But of course, you keep some stochastic term here that I didn't want to write. They are not too difficult. So this is not a closed equation now. Actually, this you cannot completely reformulate them in terms of not in a nice way, at least I should say. But this is okay because you apply a law of large number and you see immediately that this term has to go to 0. And you have rates. So this is a very similar type of situation. And the fact that the dynamics is random is not really, and that you have this term is not really the problem. So this is a sort of strange SPDE now instead of the PDE, but it's mostly the same type. So this is what I was saying. What you were expecting is that in some weak topology, you have convergence. And you have convergence to a solution of that guy with an initial data, which is the limit of the initial data. And so I can even formulate the problem. The initial data, I chose them, so I can assume that I have a sequence of initial data such that the corresponding object has a limit, and then you want to show that this is true. And this is not too scary because at the continuum level, this is an equation that we understand fairly well now. And in particular, in dimension 2, in dimension 3, you have existence, uniqueness, well-posedness, nice stability results. Everything is going well. Okay, so let me show the same macroscopic models. So now it's the same trick, right? So you have something like that. Here I have a load for a small dependence on each guy, essentially because I want to allow those to be +1 or -1. So I want to allow to have a mixture of guys that are attracting each other and guys that are repulsing each other at the same time. And now there's a small trick that I actually introduced, and there's one over n missing here, sorry. I'm actually introducing the mu I in the empirical measure. So the empirical measure is not necessarily a positive measure. You do the same calculation as before, and this is the candidate for a limit that you have. With the limit of this guy, so it's 0 or whatever it is. And now if I'm putting this in the 2D situation with K, the Coulomb interaction, this is 2D Euler or 2D Navier-Stokes. So you may not be so used to see the equation written in that form. That's the vorticity formulation in dimension 2 for Euler or Navier-Stokes. So it's a very well-known model. And this is actually a point vortex approximation for 2D Euler or 2D Navier-Stokes. So it's a very well-known type of problem in statistical physics, almost as old as the case in phase space. It has been used a lot for numerical simulation. I mean, it's a whole field in itself. Of course, again, you can change the kernels, and you still have tons of interesting models here. But you cannot get 3D Euler or 3D Navier-Stokes like that. Okay, the vorticity formulation is not as nice as this anymore in 3D.
Is that a convolution this time?
Yeah, so it's convolution of K with rho multiplied by rho. And so without diffusion also. Okay. So this is the first way of saying things. Now I'm going to take another approach through statistical mechanics. And we are going to start by what is called the Liouville equation. So the Liouville equation was actually not derived by Liouville. Liouville just showed that the measure-preserving part of the dynamics. This equation was obtained by Gibbs a few decades actually after Liouville proved the propagation of measure. So it's simple enough. Now I'm going to take a statistical point of view, and so I will want to write an equation on the joint law of the dynamics. Okay, so let's call that object Ln. And you see that Ln depends on the n variables, right? So this is the probability density of finding a solution x1, v1, xn, vn, and in at the corresponding positions. And it satisfies a very simple PD. Okay, so this is the x dot equal vi. This is the vi equal the sum of, right? And here you have a diffusion. Now, of course, it's a completely deterministic problem. There's no stochastic term here. Okay. And even if I choose random initial data, on the position, then this is just embedded into Ln at t equals 0. Right? If I choose just one condition, then Ln at t equals 0 is some Dirac mass at the corresponding position. And if I choose random, then it's the law of the initial condition that is here. And in the macroscopic case, you have that. So the Liouville equation is very nice. You have all the information about the dynamics at this level. The problem is, this is again an object which lives in a very large space, in a space which increases with n. So I cannot really pass to the limit into that. So this is not quite true. There have been efforts, but then you go to an object which is defined as a measure of measure. So let me not enter into this. Okay. And this is the case without stochasticity. You just lose the Laplacian. So instead, you have the following idea. Let's not look at all the joint. Yeah.
Sir, what do you mean by macroscopic case? You talk about macroscopic.
Oh, macroscopic case is the case order 1, and phase space is the case order 2. Right. So you see, this comes from the dynamics at order 1.
Oh, so
this is the macroscopic case. Okay. Order 1, and this is. And this is the phase space, order 2.
Okay, so you integrate out the velocity.
Yes, yes, yes. It's the the phase space. I should call it mesoscopic, but most people are not very familiar with that. Okay, so this leads me to the concept of marginal. A marginal is not the joint law, it's just the law of a fixed number of such objects. Again, remember that everything is invariant by permutation, so it doesn't matter which one I'm taking, okay? So you choose k out of the n, and you write the law on those k, which, again, if I have the joint law, simply means that I'm integrating with respect to the n minus k other variables. And here again, this space is either r to the power 2d or r to the power d. Now, this is a big simplification because the marginals live in a fixed space. This lives in a space of dimension k, or 2dk. That's it. The dimension does not depend on n. So now again, I can start playing the game of trying to pass to the limit for a fixed k as n tends to plus infinity in each of those guys. You might say, okay, so those are two formalism and there should be some way of connecting them, and yes, there is. So you have this formula. So essentially, the k marginal, you can see it as you tensorize k times the empirical measure. You take the expectation of that, and this is your k marginal, up to a lower order term. So this happens when in this product several guys, several Dirac mass, or the same Dirac mass is showing up several times. Right? This is a sum of Dirac mass, so you can decompose it into a sum of product of Dirac masses. As long as they are all different Dirac masses, then you get this. And whenever you repeat one of them, then you don't get that, and this goes into a smaller order term. So information about the marginal is really information about the expected value of products of the empirical measure. So this contains more than just the expected value of one empirical measure, and that's important. I had an equation on the joint law, so if I integrate this equation, then I will get equations on the marginals. And this is it. Okay, it's a little bit painful, but so let me guide you a little bit through it. Well, this is derivative in time. This is just you integrate, and that doesn't change. The problem is when you integrate the terms with the interactions. And then you have essentially two possibilities. Either the positions that were in this term, well, they are between 1 and k, and in that case they are not integrated at all, and you get a closed form. Or they were one of the later position, and then you get a non-closed form. Okay, so this is again a very simple calculation to make. The diffusion doesn't change. When you're going to the limit formally as n tends to plus infinity, you see that this term disappears. This term disappears because I have k terms here and essentially k there. So this is like k squared over n goes to 0 as n tends to plus infinity. That one remains. So when you pass to the limit, this is the equation you obtain, and it's called the Vlasov hierarchy. And why is it hierarchy? Because it's not closed. The equation on Lk involves Lk plus 1. And the same thing happened before you were passing to the limit. The equation of Lnk involved Lnk plus 1. So if you want to work with a guy like that or a guy like this, you need to consider all of them. All infinite countable number of them. Mathematically, this is a horrible system. Really a horrible system. Now, let me go to the key concept. So we had a nice candidate, right? This was the Vlasov equation. And this was our candidate for a limit. So now I'm going to ask, where does this guy fits into this infinite number of equations? Well, so I have this hierarchy, hopefully, at the limit. What's the relation between the two? If the solution to that is tensorized, so you put this as an ansatz into this hierarchy, and it will be a solution if and only if the f here is a solution to the Vlasov equation. Again, this is a fairly simple calculation. So this is what we are hoping to have solutions here that can be expressed under that form. This property is called propagation of chaos. And more precisely, propagation of chaos means that if initially my choice of positions, velocities were independent, this is the joint law, so the fact that it's a product is independence, then at the limit it will remain independent. The key difficulty here is that it cannot be true before you pass to the limit. So if I go back to there, then I cannot, right? It's not that I cannot prove. I cannot have a solution to this, which is a tensor product. And that's because with a finite number of individuals, you have correlation in the dynamics. This is unavoidable. So let me summarize a little bit the two main questions that we arrived at here. So we have the mean field limit. The mean field limit means that you start from a given sequence, generally speaking, deterministic sequence of initial conditions, and you have to prove to me that the empirical measure converges to the right solution. So this may depend on the choice of the initial conditions. Right? Maybe it works for some sequence of initial conditions and it doesn't work for other sequence of initial conditions, which is actually what happens. Propagation of chaos essentially means that this type of result will hold for almost all initial conditions. And almost all with respect to what measure? With respect to a tensorized measure like that. In particular, if now I take random initial conditions, propagation of chaos, because you have to converge to a deterministic object, the final equation has no stochasticity in it. Propagation of chaos means that the randomness should vanish from your empirical measure. So the empirical measure minus its expectation should converge to 0. And you can actually check that this is equivalent to having a form like that on any marginal. So this property will be true on the marginal if and only if this is true. The connection between the two are a little bit obvious, right? So if I have mean field limit for every initial condition, then I have propagation of chaos. And if I have propagation of chaos, then I should have the mean field limit for almost all initial conditions. But in general, sometimes you can prove one and not the other, because they are not identical. Is everything okay till now? Okay, so the last part where I'm going to go a little bit fast, I wanted to show to you at least a few results there. Very classical ones. So the first one is the oldest. It's due to Dobroshin, Bond, and Hepp, and it was formalized very nicely later on by Spoon. And so this is 77. Gives you the order of magnitude. And it's the Lipschitz case. And in the Lipschitz case, I have a very nice result which goes even beyond the mean field limit. I have a completely explicit stability result on any measure-valued solution to the Vlasov equation. So measure-valued solution includes solutions that are empirical measures. And it's a stability estimate with explicit constants, as you can see it here. So it's written in a weak norm, and given that those are measures, again, you have to use weak norms. Typically nowadays people use Wasserstein distances to write this. But this is the historical version. So this gives you much more than just convergence. It's still probably not optimal, especially this exponential growth rate in many settings is rather doubtful. But it controls all statistical property of the cloud of particles, and the constant C here is explicit. Essentially, it's the total mass. So that's very, very simple. I write this in the phase space case, and then non-random. It's the same with stochasticity and things like that. The proof, I'm going to go very fast on it because I'm kind of late now. The proof, essentially, you've seen it. I showed it to you when I showed you the well-posedness in the Lipschitz case, and when I showed you a result which was independent of the number of particles. And this is the exact extension of that result, except that now I have to put a lot of structure on it. So instead of defining a system of a discrete system of ODE, now I define a family of system of ODE by the characteristics like that, and you see that it's exactly the same kind of equation. And this is well defined because this guy is Lipschitz, and you have tons of very nice regularity assumption on that. And now the key thing is this W minus one norm. You can rewrite it using the system of characteristics by something like that, where this is the initial condition. So now if I can have a good control, the distance between the two systems of characteristics, I will get the result. Again, I'm probably going a little bit faster than I should here, but so this is essentially what I'm saying. Now you're doing the decomposition, and you get something like that, meaning that the difference between two solutions at time t is bounded by some regularity of a system of characteristics times the initial distance plus the difference in the characteristics. And the difference in characteristics, so you do exactly the same trick as before. You take the two solutions, you subtract, and you write down a Granville lemma. And it really works in a very similar manner, so let me skip the calculations here. Again, this is not a very complicated result. You get a Granville estimate, which is like that at the end, which gives you the result you want. Now, let me go to another discussion, which is so in the phase space result, in the phase space case, the result I've just shown you has essentially remained the best result till very recently. And when I'm saying it's the best result, it means so we have a recent paper that does better than that, but it's the only paper. In contrast, if you're looking at the macroscopic case, most practical cases were solved in the 90s. And this is a little bit weird because if you're thinking Euler equation versus Vlasov equation, for instance, you're thinking, but Euler equation is harder than Vlasov equation. So why should the limit be easier? And this is a structural question. And the key here is to realize that if I'm looking at the singularity, in the kernel, in the phase space, then the singularity is whenever x is equal to 0. So it's actually here. The whole plane x equal to 0 is a singularity for the kernel. In the Euler case, well, this is x, and this is x as well. The singularity is very nicely symmetric here. And this difference in topology between the two singularities, this is what makes your life easier. So here's an example of strategy in the macroscopic case. You control the minimum distance between the particles. And by symmetry, you can show that as long as this minimum distance is of the right order, and I've written the order here, then the force is actually smooth. So you have estimates like that. The Lipschitz norm of the force term can actually be controlled by some function of this minimal distance divided by the right scale. And then you just use that to propagate the minimum distance. So you choose 2 points which realize the minimum distance, and you see how much closer they can get. That, and well, so this is the force acting on each one of them. And that's here that you gain the fact that you're order 1. The velocity is equal to the force. So if you're close, the forces are close, therefore your velocities are close, and therefore you cannot get much closer. You get something like that. You replace this by this estimate, and you have again a Granville type of control, at least for a short time. The problem when you're going to second order phase space model is that the force is still controlled by the minimal distance in physical space. But this is not true because it's second order. What the force controls is not the minimal distance in physical space, but the minimal distance in phase space. That guy. And again, there's a really good reason for that. For second order models, you have collisions between particles. You cannot avoid them. And you do not have them for first order models. So the 2D Euler, for instance, you can see those papers. So this is early 90s, this is late 90s. It's time. To conclude. So let me summarize a little bit what I've talked about here, very roughly. When the interaction kernel is Lipschitz, essentially we understand what's going on. And you can prove propagation of chaos, you can prove the mean field limit, you can do it in the various settings that I've shown to you, and you can actually do it in other settings that I've not shown to you. The other case where we understand relatively well what's going on are the deterministic and macroscopic models. So first order deterministic case, because of the structural property, we know fairly well what's going on. And we have a very good control on how particles are behaving. Still in the deterministic phase space model, well, this is the best result that we have now. And we can only handle the singularity, which is of order 1 over x. This does not depend on the dimension, okay? So it's alpha strictly less than 1 in dimension 2, and it's alpha strictly less than 1 in dimension 10. And the reason for that is that we need to integrate the force term along trajectory are one-dimensional object, and this needs to be integrable. So what's the singularity you can integrate along in 1D? It's that, okay? And there are physical reasons for this as well. This is the case in the potential case, for instance, the energy is bounded, so you don't have real collisions. Let me not go too much of these details. What's more interesting is now, if you're wondering, yeah, what about the stochastic case now? It should be easier. Well, what about the stochastic case here? Nothing. Absolutely nothing. This doesn't make any sense in the stochastic case. If those guys follow Brownian motions, at least in dimension 2, there's every reason to believe that they can get pretty much as close as they want. This will not be of order n to the 1 over d, this will be 0. Or very, very small. The whole thing breaks down. Actually, the stochastic case is the worst of them all. And it's mostly empty. So mostly, so here there's a few exceptions. 2D Euler is understood in the stochastic case. And actually there are scaling reasons which explain that things like that, you should be able to understand them. But this is a stupid Sobolev embedding, so it's not a very good or convincing type of reason for why you should control stuff. So this remains mostly open, and anyway, nothing at all is understood if you have alpha n going to 0. So if you have a diffusion coefficient that scales with n and that vanishes at the limit, then no one knows how to do anything. I hope I didn't bore you too much, and thank you very much.
Thanks a lot for this very nice and interesting talks. Are there any questions, remarks?
It's probably a bit too technical at the end.
So I was wondering.
So you briefly touched on some type of cosmological models that
Yes.
people were using. So these are on, you mentioned sort of scales of galaxies.
Yeah.
Yeah. What time are they using?
So the scaling changed a lot, depending on the setting. But the basic idea in cosmology is you want to understand, for instance, at very large scale where matter will concentrate. And for that, what people typically do is they take Newton's dynamics, at least in the case of spatial relativity. We don't want to get speeds that are larger than the speed of light. And they solve that for large times. And this shows concentration. And they say this is the beginning of the universe, when things were dispersed and they start to concentrate. And where you have the concentrations are, you know, the solar systems, the galaxies, the galaxy clusters. A variant of this type of calculation is to say, so you have dark matter, and you have more dark matter than you have matter, according to current measurements. So dark matter is responsible for those concentrations. So people solve the first system for dark matters, and since they are saying that dark matter, whatever it is, we don't know, only interact through gravitation, because that's the only way we can detect it for the time being, then they are fairly confident that they can solve the system for as long as they want. And then again, wherever the dark matter concentrates, they are saying the gravitation there is going to be huge, so this will attract normal matter. And again, that's where you will have galaxy clusters and things like that.
Does this take into account evolution of the space-time?
No, so this is mostly special relativity.
Okay.
But again, for good reason, at those scales, the density of matter is not large enough to create relativistic effects. So strangely, so you really have the two scales, right? The scale at the solar system or things like that, where you can also get very good results with Newton dynamics. And the very large scales, you use again Newton dynamics, and of course in between concentrations of masses, then you have to use general relativity. You can ask similar questions with general relativity, but then it's even more horrible than whatever I have shown.
I'm trying to relate your results about the joint distribution being the product of the marginals for the case of an ideal gas. If you take an ideal gas with relatively low pressure, you've got essentially pairwise interaction, it's repulsive at short distances.
So this is exactly the Boltzmann ansatz. Molecular chaos. For a different reason, because Boltzmann equation to collisions, which is what you're expecting to have, so very short range.
Right, repulsive.
Repulsive should behave differently than the sort of long range weak interactions that I've shown you here. So those are really two different type of settings, but the formalism is exactly identical.
What was the restriction on K you put that excludes considering?
Oh,
ideal
if you
gases?
want to do Boltzmann, then you have to scale K. So I can derive Boltzmann from that, but this is the wrong scaling now. I have to put an N here. So I have a range of interaction which depends as well on the number of particles. And then I will get collisions, and you will get hopefully fluid dynamics at the very end. But
So my follow-up question is no longer relevant. I was wondering, in the context of an ideal gas, if you try to make N large, do you do that by making it a bigger container or by increasing the density?
so it's a question of rescaling here.
Right.
It says, and what I should say is that the formalism that I showed to you was mostly developed at the time for Boltzmann. So for this different scaling. It turns out that you can use it to express the results here. Where things completely bifurcate is when you're actually trying to prove something. So at the level of the formalism is very similar, but whenever you actually enter into the details, then they are.
Well, we're running out of time, so we can continue the conversation during the refreshment. Let's thank Pierre-Emmanuel again.